Energy is a central concept in all of science, yet it is a little bit hard to define. In fact, in the book we use, they throw in the towel at the introduction. They say, unfortunately, despite its extreme importance, energy cannot be easily defined. So everyone that's taught intro physics has had this moment where they think they've come up with the first great way to explain energy, because you're thinking about how, well, it's really the capacity to make something happen, and then it hits you. The analogy that's going to make you famous. Energy is the currency of physics. Currency meaning money. That's the best way to think of it. If you have a lot of money, you can make a lot of things happen in the world. If you have a lot of energy, you can make a lot of things happen in physics, and you congratulate yourself on how brilliant you are, and you look at some textbooks to see where they should bring this analogy in, and you see everybody already uses this analogy, very common analogy. My favorite is one book, goes on for about 3 pages with this analogy, takes it way too far. There's like a central bank, there's a Federal Reserve, ridiculous, okay? But the basic idea is pretty useful. Energy is the currency of physics. What I'm going to do is go straight to the first kind of energy we want to talk about. Rather than more philosophical money stories, let's go straight to kinetic energy. Kinetic energy is the energy of motion. Very common definition for kinetic energy. And let's go straight to the mathematical formula. It's K is what we're going to use for kinetic energy, just K, not KE. It's too much writing. Is 1/2 the mass v squared. And since it's squared, and since energy is a scalar, and we're not thinking about a direction or a vector, it's just really the speed. 1/2 mass times the speed squared. It is in, we can get the unit, kilogram meter squared per second squared, which is equal to a joule. So the MKS unit for energy is the joule, which is abbreviated big J, right? Let's see. So I'm going to give you an example of what it means to have a lot of kinetic energy, right? If I have kinetic energy, I can make things change. I can cause strong interactions. To have a lot of kinetic energy, I need a lot of mass, and I need a lot of speed. So what I'm going to do is I'm going to bring in this. I'm going to have an interaction with this, and since I'm going to have a lot of kinetic energy, I'm going to make a big change in this object. That's the idea. So let me see. I'm going to be on a cart, and we're going to see what kind of interaction I have with this object. Now, if I have just a teeny bit of kinetic energy, let's see what would happen. Low velocity, low kinetic energy. That's all that happens. But now, let's see what would happen if I have a lot of kinetic energy. Aim it just right. All right, so we had a lot of kinetic energy. We made a big change. And let's see, we could even estimate how much kinetic energy we had. Here's the cart. Here's me. Woo! And K would be 1/2 my mass. We'll call it 70 kilograms. We all know it's higher than that. And my speed, I was probably going maybe 3 meters per second. 3 meters per second squared, which gives me 315 joules. So I had about a kinetic energy of a few hundred joules. So now, before we move on to using it, let's do just a few bullet points about energy that you may wonder. Things that make people say, is this true about kinetic energy? The first one is, I'm just going to answer them. I know they're in your head. Yes, K is always positive. You can only have positive kinetic energy because M, mass is positive. You square the V, it's always positive. The half is always positive. Later, we'll have changes in kinetic energy that could be negative. But the actual value of the energy itself, it's always positive. 2, yes, K is absolute in a reference frame. We'll clarify that in a minute. But you'll see things like potential energy, other kind of energies are coming later, or position on an axis, depends on where you put 0. None of that is the case for kinetic energy. You have a certain amount, no matter where you put the origin. Okay. 3 is yes. The absolute value, the value, I'll just say value to not cause problems, the value depends on your reference frame. So this bothers people because you think, well, energy is conserved. We only have a certain amount of energy. It can't change. But it is actually different in different reference frames. When you were sitting there and I flew by, I had 315 joules of kinetic energy. But if somebody else was on a crash cart going the same speed looking at me, it looked like I was still, I had 0. And they had 0 to me. We both had 315 to you. So it does change when you change reference frames. We're not going to get into that part too much. To keep up with energy, we have to talk about work. Work is how you exchange energy. And following the financial analogy, it is the ATM of physics. Now that one might be original, I'm not sure. But it's where you put money in, take money out. Because some people do put money into the ATM. The people that show up with all the checks and hold up the line, yeah, you know who you are. So it is the ATM of physics. It is also a scalar. It is also in joules. It's the same as kinetic energy in J, in joules. So units are the same. Everything's the same, except you don't really have work. You do work, and you do it to exchange energy. So let's see. To do work on an object, you push with force, we'll call it F, through displacement. And we'll go back to our delta R notation for displacement. It doesn't have to be a mechanical push. It could be a different kind of force push. But for now, we'll just think about sort of a mechanical version. The formula for it, work, W, it's a scalar. And it's F, that force you just applied, dotted with that displacement you just went through. And if you do work on something, you will give it energy. The only kind we talked about so far is kinetic, so I can show you an example of me giving this little car kinetic energy. So we'll say I'm going to push, I'm going to start here, and I'm going to push and apply a force till I get here. Okay, so this is my displacement right there. All right, so if I do that and I push constant force, what did I do? I gave it kinetic energy, right? And I applied a force, a constant force, through this displacement delta R. It went a lot further, but the only part that counts is the displacement over which I applied the force. It doesn't matter that it keeps going. It's definitely going to keep going. I gave it kinetic energy. But it's this delta R here, and it's the force F I applied that matter, F dot delta R. Now, one thing about this, for now, this is sort of only applies for a constant force. Later, we'll get into what to do if the force changes with position. Okay, so let's think a little bit, in case you haven't done one in a while, or ever, about the dot product. Dot product multiplies two vectors. So far, we have multiplied a scalar times a vector, Newton's second law. Sum of the forces vector equals mass scalar times acceleration vector. But now we need to multiply two things that are both vectors. So dot product is one way of doing it. So to figure out a dot product, we need the two vectors. We could write the force vector like this, Fx I hat plus Fy j hat plus Fz k hat. Of course, the one I just did was in one dimension, but it could be written in 3 dimensions. And then delta R vector, well, that's just the 3 components. Delta x I hat plus delta y j hat plus delta z k hat. So you need both vectors fully described to take a dot product. And then you can kind of decide if you want to do it in Cartesian coordinates or polar coordinates. So some problems are set up one way, some are set up another way. Cartesian is for when you have those components. If you're given these x, y, z components, then this is what you'd want to do. The dot product is F dot delta R is basically you just multiply the x components plus the y components plus the z components. And it's no longer a vector. So a dot product of two vectors makes a scalar. Right, so it would be Fx times delta x. Right, multiply those plus Fy times delta y plus Fz times delta z. And whatever you get, That'll be a scalar, and that'll be your dot product. But actually, I'd say in most problems, you're given them in polar coordinates. You're often told you have a 10 Newton force at this direction, and then maybe your displacement was 30 degrees away in this direction this far. Right? In that case, you write the dot product this way. You say F dot delta R, which is going to be a scalar, is the magnitude of the force vector times the magnitude of delta R vector, the displacement, times the cosine of the angle between them. That also gives you a scalar value, and that is also going to give you the same thing you would get here and here. Just depends on what you're given as far as which one you want to use. Now we'll calculate the work in a few cases, and we're going to use the force of gravity rather than me pushing so that we can actually calculate something. So first we're going to do drop and shoot. So you remember drop and shoot, 2 blocks and one fell and the other got shot and they landed at about the same time, right? So we'll look at drop, look at the work that gravity did, and we'll look at shoot. And for all of these, since we're doing now vector dot products, we need to be careful with our coordinate system. So let's put positive x this way, positive y this way, which means positive z has to be out. X cross y is how you find the z direction. Let's see, in drop we had the case that we had a mass here, mass m, and it basically just falls through a displacement d. Right? Or let's call it delta r, just to match our previous notation. And we could say, what's the work by gravity? Well, the work is F dot delta r. So the force of gravity, F, is what? It only has a y component, right? So it's 0 I hat minus mg j hat plus 0 k hat. Right? And what is delta r, if we want to write it as a vector, is, let's see, in the x direction it's 0 I hat, and it is, we dropped a distance d. I meant to say that's the displacement vector, but we dropped a distance d. Right? So the displacement was negative d in the j hat direction, and we didn't move in the k hat direction. So to find the work using our Cartesian definition of the dot product, then it would be just this times this, 0 times 0 is 0. It would be minus mg times minus d, right? That's mgd, and then the two minuses turn into a plus. That's just a scalar. Plus this one times this one is also 0. So the work is mgd, the work that the gravitational force did on the object. Now, although, let's look at shoot. Right? So shoot was the one that we shot it with a little bit of an initial horizontal velocity. It also fell through d, but it kind of went like that. Right? And it made it through some distance, the range. So we'll call that r. But we'll still keep this as the origin, just like we did before. Okay? So let's calculate the work in this case. Let's see. So the force again is only minus mg in the j hat direction the whole time. There was no force in the x, it just had an initial velocity in the x. And the delta r, the displacement, was, let's see, everything's negative here. It was, no, it's positive r I hat minus d j hat plus 0 k hat. All right. So here's your two vectors. And if we want to do this one Cartesian, why not? We would say the I hat components, well, it was 0 here. 0 times r is 0. So the fact that it moved that direction doesn't really help us any. The work, 0 for the I hat contribution, minus mg times minus d, mgd, for the y contribution, and then 0 times 0 is 0. So you see that gravity did the same amount of work whether you dropped it or whether you shot it. Talk about what that means in a minute. Let's do one more. Let's do a ramp. So here I have a one-dimensional ramp set up, and Frank is going to roll down the ramp for us. Okay? So Frank is here. He's feeling a gravitational force, and it's going to push him down the ramp So we're going to figure out how much work is being done down the ramp. Here we go. So let me draw that real quick. So it looks a little bit like this. Let's imagine it went down the same distance d. And let's say the ramp is at an angle theta. Right? And he went down like there he was, like that. Moves down the ramp. Let's see. So this is a case where we want to maybe think about doing it in polar coordinates, just for fun, right? So if we think about this, then the displacement would be this vector, all the way from here, all the way down to there. There's delta r. And the force, well, the force, of course, mg is down. There's a normal force up. In the end, you get an unbalanced component that pulls you to the side. You get mg sine theta. So the force pulling you down is mg sine theta. So let's think about doing the work the polar way. Work is the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. Well, let's see, look at it. Let's see, the magnitude of the force is mg sine theta. Okay, we have a sine theta, even though it's not this theta. It's because it's just a component of the force. The displacement is what? It's not just d. You got to go with the actual displacement. You got to force this way. We have to go this way. We have to know what this distance is. Well, sine theta is the opposite d over the hypotenuse. And this is a case where we actually want the hypotenuse. Usually you're given the hypotenuse and you break it into components. This is a little different. We're given one of the sides. So actually, the hypotenuse we want is d over sine theta. D over sine theta. That's the magnitude of the displacement. And then we need the cosine of the angle between them. Cosine, what's the angle between them? 0. I'm doing this down the plane. I'm not breaking things into components. Cosine is 0. And that's just 1. Right? So that's 1, and those two cancel, and you get the same thing, mgd, every time. Right? So the point of this, what you're supposed to notice is if the mass, if the force is really down, okay, and if the mass moves a distance d down, it doesn't really matter what else it does. In this case, it moved a distance d down, mgd. In this case, it also had some horizontal component. It doesn't matter, there's no force that way, mgd. In this case, we didn't even treat the forces down. We calculated the component this way, and it still came out, mgd. So that's why sometimes you'll see this written in books as, I don't know, the work is like the force parallel times the distance that it goes. And what that means is it's the force, or it's the distance along the force direction or something. But what they're really trying to find a way to say is it's the dot product. The dot product gives you the component of one vector along another, and all that really matters in work is how far did it travel, what was this displacement along the actual force. And that's what we got here, 3 different ways.